Okay, we talked about how great it was if we could find an element if the array was already sorted, but of course it needs to be sorted beforehand. We haven't talked about how do you actually sort an array. Do you need to call different sorting routines? There are a lot of sorting routines. With searching an array, usually you have binary search and linear search are basically your two options, unless you are doing something really tricky. With sorting, you have many options in order to sort. We're in this class only going to cover 5, the 3, I'll say naive methods, and then the 2 standard in-log-in methods. But first, we're going to study the very naive one, which is called bubble sort. So you have a sort from, you have a list, O to N, they're in some elements, and you want to, what we do? In a series of n-1 iterations, compare successive elements, list to list, yeah, up there. If it's greater than, swap them. The beauty of bubble sort is how simplistic it is to code. The downfall is it's the slowest. But let's go take a look at it pictorially, and you'll understand why it's called bubble sort, because it's bubbling. You start at the top, up here. You compare the two. Is 10 greater than 7? Yes. Now notice in the end we want to have the largest number at the bottom and the smallest up top. So it's bigger, so you're going to swap them. It's going to compare the 10 and 19. The 19 is bigger. Don't do anything. Compare the 19 and 5. The 19 is bigger. Swap it down. Compare the 19 and the 16. 19 is bigger. Swap it. 19 is now in the correct spot. It's called bubble sort because each time you iterate, you're going to bubble up the highest element to where it needs to be. So 19 is in the correct location. You don't have to do the whole array. You do the whole array minus 1. So we start again, 7 and 10. 10 is bigger. Don't do anything. 10 and 5. 10 is bigger. Swap them. 10 and 16. 16 is bigger. Don't do anything. 16 is now in the right location. 7 and 5. 7 is bigger. Swap them. 7 and 10. 10 is bigger. Don't do anything. And the last two happen to be in the correct location. All right, y'all get the idea? We're going to do the analysis. All right, analysis here for comparisons. Total number of comparisons. Well, you have, actually, let's go write this. You want to write the code for this? Yes, okay, good. Let's do int bubble sort, int array, int size. Okay, so what are we doing? Well, I'll give you the first hint. You have 2 for loops. Woo. All right. Okay, so as we're going down, what do we do?
So how can we start at 0 and at like the last index of the last variable? Because if we're going to compare, we're either going to compare the variable, the
Value afterwards.
The value before.
So there are different ways to write this. So yeah, let's start at 1, just for now.
So if the array of j is less than array of j minus 1.
J minus 1 is less than, or let's say, I think I'm doing it backwards in the way you just said it. Sorry about that. Then you need to do what? Swap them?
Yeah, like this temporary.
Yeah, we'll do the swap. At some point you'll hopefully learn about XOR swap, but we're not going to do that right now. All right, that's it. The beauty of this algorithm is how easy it is to code. That is pretty much its only advantage. But that's it. Just go through the list, compare and swap them. So let's go and mess around with that for a little while just to see if it's working.
That's because of the swap. makes it inefficient?
We'll go in and do the analysis. First, let's make sure our code's working so we can look at the code and actually do a proper analysis of it. All right, give me numbers.
3. Well, -3. 42. 73.
-8. Nobody thinks -8.
And 9,001.
8.
What was it? 1? All right. All right, we're good.
Is this one of the, this kind of be like 2 to the end, kind of, as big as it gets?
Is it
One
squared?
big.
It's going to be in squared. Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Let's go ahead and print it out. Oops. So 2.
Wait, why did you know the second?
Good catch. Anything else? Let's see if we coded that right. Hey, look, it worked. All right. Welcome. All right, whoops. That was the jumping ahead a little. So we have some confidence it's working. All right, what's the big O of this? Oh, you know what? No one did that, right? Because once the last element is in the right place, we don't need a bubble anymore. Let's go make sure that that is correct. Okay, good. So that might help a little. So how many times does this loop iterate? Yeah. Okay.
Size minus I, so it means size minus.
Yeah, so this iterates how many times? Basically n minus I minus 1.
So the worst case scenario would be n.
Yeah. All right. Always performed. Sorry. The compara. Oh, how do you spell comparison? Wow, I'll just say the compare is always performed. There we go.
Why is it n minus I minus 1? Why is it, what's the minus 1 for?
J starts at 1,
Whoa.
not at 0.
Yeah.
Okay. So what's the big O of this? Yeah, well, yeah, so it's basically n times, n times n minus I minus 1, which is basically, I'll go, there we go, O of n to the second power. Y'all see that? Yeah. All right. Okay, and that's where the number of comparisons, how many swaps would happen? Because the swaps aren't happening every time.
Yeah, so like maximum.
Yeah, the maximums could happen every time possibly, or it could never happen. But on average, it'd probably be somewhere in between, so it's n squared divided by 2, which is still n squared. All right, let's go and look at the slides. I think they go through this a little more. Total number of comparisons. Oh yeah, for each one, because at the first one you're doing n minus 1 comparisons, because that's the inner loop, n minus 1 times, then you're doing n minus 2, then n minus 3. Remember our amazing formula? Well, except for it's minus 1, you don't do that last n, so it's n times n minus 1 over 2, which is still big O of n squared. Number of assignments, right, inside the swap, because inside the swap you do 3 assignments. So it's basically 3 times this, which is still n squared in the worst case. Everyone following this on the board? Oh, that's it. Okay, so that's it for bubble sort. Great. Okay. Oh, good. We're going to finish early. Let's see. Any other good questions? I think that's it for now. Can you perform a binary search on a sorted linked list?
On the sort?
Yeah, what if we sorted the linked list? Can we do a binary search?
Yeah, why not?
That's
I have some yeses. Anyone saying no?
Is it gonna be one of those things where yes you can, but you shouldn't?
Negative.
because you can't just divide the mean you can't like divide the size by 2, go to that index. You have to like iterate through the entire.
Right. Everyone got that? A linked list, you have to iterate through it to get to the halfway point, which totally defeats the purpose of a binary search, because a binary search can just jump to that location. So this is an advantage an array has. This is actually a significant advantage, is that you can randomly jump to any location inside the data structure. The linked list, you have to iterate through it. So a sorted linked list, if I were to go back up here, sorted array. We could do a binary search, or binary sort, sorry. By binary search, I mean bubble sort. Whew. So if we had a sorted linked list, what's the big O of a sorted linked list? It's still O of n. You can't do binary search. It's O of n. There's not much you can do about that. All right. Any other questions before we do the lab? All right.